Namaste, my name is Bhaskar Kamble. So, in this video, I'm going to talk about some aspects of Hindu mathematics, and this video is the first of a series of videos which I plan to make in the coming days. And I've named this series as Gems from Hindu Mathematics. And in this video, I shall be talking about concepts like the Chitighana, Varasamkalita, and the Meruprastara, which come in various fields in Hindu mathematics, in various texts of Hindu mathematicians. So before I begin, just a bit of a background into this. So I have recently written a book on the history of Hindu mathematics, and this is going to be published by Garuda Publications. And while researching for this book, I came across a lot of information which was very interesting, and which, of course, given the volume of the information, it was not possible to include everything in the book. So some aspects I would like to communicate in the form of such presentations, and that is the purpose of making this presentation. So regarding the book, you can follow Garuda Publications on Twitter. So the Twitter handle is Garuda Prakashan, and you can also follow my Twitter handle, which is Meruprastara, for getting updates about this book. And yeah, and I think it is only fitting that my Twitter handle being Meruprastara, I should be starting the series with a related concept, with the related fields, with the related ideas. Okay, so in this, I also want to mention that this presentation has been divided into three parts, I will talk about on part 1 today. But just for the overview, I shall also give information on what part 2 and part 3 contain. So part 1 speaks about basic things like arithmetic progressions, the sum of the first n numbers, and the generalization of this concept to the sum of the squares and cubes of the first n numbers. And we will also look at a way of generalizing this to the case of the kth powers of the first n numbers, natural numbers 1, 2, 3 till n. Part 2 will discuss about another generalization of the series 1 plus 2 plus 3 till n, which is called Chitighana in the words of Aryabhata. And I will also look at Aryabhata's expression for the Chitighana. And then I will also introduce a further abstraction and generalization of the Chitighana by Narayana Pandita in the 14th century to the concept of Varasamkalita. And yeah, and then I will investigate the issue if there is a general expression for the Varasamkalita which is available, and this will form the topic of part 3. So where we will approach this problem from the direction of combinatorics and from the idea of the Meruprastara to get a general expression for the Varasamkalita. Okay, so let's go into part 1. So part 1 starts off with the ideas of arithmetic progressions, and this was given in the Aryabhatiya by Aryabhata in the 4th and the 5th, in the 5th and the 6th centuries, in verse number 19 of Ganita Pada. So his verse goes like this: Ishtam vyekam dalitam sapurvam uttara gunam samukha madhyam ishtagunitam ishtadhanam tvathavaadyantam padardha hatam. Okay, so here is the translation which I will skip. If you can of course pause the video and have read the translation, but I think it will be faster if I just go to the mathematical content of the verse, which is given by this formula. So in this formula you can see that Ti is denotes the ith term of the arithmetic progression, and the arithmetic progression has A as the first term and D as the common difference. Then the sum of the first n terms is given by this expression. So A plus D times n minus 1 over 2 times n. So this is a very well-known basic formula, and it's in high school this is very standard material in mathematics courses. So you can easily apply this formula to the case of the first n natural numbers. When you just have to see that, you realize that this 1, 2, 3 till n is an arithmetic progression with 1 as the first term, and the common difference is also 1. So A is equal to 1, D is equal to 1, and when you apply, when you put this in the formula, you get this expression for 1 plus 2 plus 3 till n times n plus 1 over 2. Now you can also generalize this to the case of the sum of the squares, cubes of the first n numbers which Aryabhatta has done, and this is no longer an arithmetic progression, and this formula we just saw is no longer valid. So we have to look at, so Aryabhatta has given a verse in which he gives the expressions for the sum of the squares and the cubes of the first n natural numbers. So it is verse number 22, which goes like this: Saikasagaccha padanam kramat trisamvargitasya shashtonshah varga chitighana sa bhavet chiti vargo ghana chitighanascha. Again, I will skip over the translation. Feel free to pause and read it. The equations are this, which the verse describes. So 1 square plus 2 square plus 3 square till n square is given by n plus 1 to n plus 1 over 6. And the sum of the cubes, that is 1 cube plus 2 cube till n cube, is very interestingly the square of n plus 1 over 2, which you will remember was the sum of the first n numbers. So this is basically the square of 1 plus 2 plus 3 till n. So these are the two results he gives. And I will just discuss how you can derive these results, starting from the expression for 1 plus 2 plus 3 till n. So starting from the proof for the expression for this. So let's see how we can prove that 1 plus 2 plus 3 till n equals what we just saw, n plus 1 over 2. There are many proofs for this, geometric proofs, very simple to understand proofs. But I will now discuss a proof which is perhaps more not so straightforward as some of the geometrical proofs you see online. But the advantage is that we can generalize this to the case of the sum of the squares, cubes, etc. So for finding 1 plus 2 plus 3 till n, you consider this sum of this difference of two summations. So the first summation is the square of I plus 1. I goes from 1 to n, and the second summation is the square of I, where I goes from 1 to n. So the first summation, that is I plus 1 square, you can open the bracket, expand this, which is I square plus 2I plus 1, and you can combine it with the second summation. So when you do that, as you can see in this slide, I square and I square cancel out, and you are left with sum over I of 2I plus 1, which is then equal to 2 times summation over I plus n. Now you can again, or you can also evaluate this sum of the differences by writing the terms one by one. So the first summation gives you 2 square plus 3 square plus 4 square till n plus 1 square, and the second summation over I square gives you 1 square plus 2 square plus 3 square till n square. And since it's a difference, you will see that 2 square cancels, 3 square cancels, 4 square cancels, and the only terms which do not cancel are n plus 1 square from the first term and 1 from the second term. So you get n plus 1 square minus 1, which is in turn equal to n square plus 2n. So now you can equate these two expressions you got. So 2 times sum over I plus n is equal to n square plus 2n. And when you do that, you are able to see immediately that sum of I is n times n plus 1 over 2. Now, if you want to find out the sum of the squares of the first n natural numbers, what do? It's very simple. You apply the same idea, but this time instead of taking sum of I plus 1 square minus sum of I square, you take sum of I plus 1 cube minus sum of I cube. And when you expand I plus 1 cube, you will see that I cube cancels out with the second term. And you can then you have a term representing sum over I square and a term representing sum over I, and sum over I we have already found out what that was. And so with this you come to the expression given by Aryabhatta, which was n times n plus 1 times 2n plus 1 over 6. And the same idea can be applied for finding sum of the cubes, sum of the fourth powers or kth powers. And the problem is that this becomes really very complicated as k increases. In fact, even for some of the squares of the first n numbers, you will see it's quite a bit of work, the manipulations to arrive at the result. And there is no general formula in terms of k, but an approximate form for summation of I to the power k was derived by the Kerala mathematicians Madhava, Nilakantha, Jeshtadeva in the 14th to 16th centuries, and this played a very important role in the development of calculus. And but that's another story which deserves a presentation of its own. So I'm going to then then this would be the end of the first part of the presentation. So in the second part we will look at Aryabhata's definition of the Chitighana, and also Narayana Pandita's abstraction and generalization of the Chitighana to the Varasamkalita. And looking forward to meet you in the next talk video on part 2. Thank you.